Morning, everyone. Your tests on Chapter 2 will cover everything from the atomic history stuff that we did, the different models of the atom, Dalton, up to the Bohr Model, looking at counting protons, neutrons, and electrons, doing isotopes and weighted averages, all the way up to the electron configuration stuff and ionization energy. Over the next 2-3 lessons or so, we're going to start a little bit in Chapter 3. Fortunately, this chapter actually sort of reiterates some of the main concepts in Chapter 2. So hopefully by going through this, not only will this give you a little bit of time just to do some studying, it also will help flesh out some of the concepts in explaining trends in the atomic radius, the sizes of the atoms, as well as the ionization energy that we ended off with. So this is officially the start of Chapter 3. If you can start a fresh new page on your notebook. This one here, we'll call it Unit 3. It's a guy we call Periodicity. Periodicity is the name of the chapter. So periodicity has the root word here, something being periodic. If you know motion that's periodic, it's motion that repeats itself. It's motion that comes in cycles. In this case here, this chapter is all about having organized the periodic table as we have in our data booklet. What are some patterns and what are some trends that seem to repeat based on where elements are placed on the periodic table? It probably shouldn't surprise you that a periodic table didn't always exist this way. This is sort of after many hundreds of years of work. We credit a guy called Mendeleev in putting this together. We'll see that a little bit in this lesson here. Some trends just right from the start as we just look at the modern periodic table. Even from that electron configuration stuff in Chapter 2, we already were able to see, say, the first two columns, okay, alkaline earth metals, alkaline metals here. We saw that the electrons that enter those are called S block. The latter 6 columns here are the P block. So elements that enter these ones here are P electrons. They're going to enter those dumbbell-shaped orbitals. We don't get our transition metal, our D block, until we have, technically this one here would be 4s, but we saw in the last chapter, by the time the Ds finally show up, this is only energy level 3D. So we have our transition metals here. This middle section here are called D block. And then the 2 rows that we actually pulled out, these ones here are called, starting with lanthanum and its row, these are called lanthanides. Starting from actinium and the row that follows afterwards, these are called actinoids or actinides. Sometimes they're referred to as inner transition metals because these 14 extra electrons should have actually been squeezed in between. So you can imagine this periodic table being spread out much wider, sort of horizontally, because we don't really talk too much about these ones here. For example, uranium, although it's good for nuclear fission, it's our last stable isotope that we have in our universe. We just sort of, in the lab, we synthetically create, doing a beta decay, we force uranium to acquire a neutron. We force that neutron to become a proton, and because proton number tells you what element you are, this is now suddenly a new element. A lot of these elements here at the beginning were just given placeholders. They only list a matter of split seconds. Physicists and chemists have run them through particle accelerators, played around with time dilation to try to study them in a little more detail, but definitely for you to know, these ones here are synthetic and these ones here don't appear normally. If we look at the periodic table as a whole, again, we'll come back to this in this lesson, we see that the periodic table is arranged sort of based on mass. We have our lightest elements here at the top. As we traditionally read left to right, as we go to the right, the mass tends to get heavier. So if you remember back to the Bohr model, we have inside our core, we have protons and neutrons, which were heavy particles. We call those nucleons. Electrons were those strange ones. Even though the Bohr model suggested that they were in discrete orbits, we found in our electron configuration model that even these orbits needed to be subdivided into those s, p, d, and f layers. As you step across, we know what makes you different is the number of protons. So say we go from lithium with 3 protons and we go to beryllium suddenly with 4 protons. Having the more protons and the added mass here from neutrons, obviously the mass here is heavier. Obviously we're now a new element. As you continue across here, what you're going to find is the number of protons continues increasing as well as neutrons. The core itself is going to suddenly get larger and larger, more protons, more neutrons. As we come back towards the end of this lesson to talk about radius, I want to emphasize again, we're not really measuring the radius of the nucleus itself. I know that's increasing. I know every time I have more protons, more neutrons, the center of it actually gets bigger. When we actually talk about the size of the atom, we actually want to measure from the center of the nucleus all the way out into the outer shell we call the valence shell. If we have multiple shells, definitely we measure all the way out to the furthest out shell, the furthest out orbital. So even though the center itself is actually increasing, we saw a little bit in the last chapter that because of that increased positive attraction in the core, the shells end up actually condensing on itself. The shells actually get closer and closer together. So those are some of the main ideas that we're going to hit in today's lesson here. We're going to start off our lesson today here with a guy called Dmitri Mendeleev. He was credited with the organization of the periodic table. So again, if you could just copy this down on your notebooks here. We had a Russian chemist. His name was Dmitri Mendeleev. Careful, this is a different guy from, say, in biology. We had a guy called Mendel that did a lot of genetic stuff. This is a different fellow. Dmitri Mendeleev, around the 1800s. You have to think about back to your atomic history structure. What did he believe the atom was? If you remember in chapter 2, between the 1800s and 1900s, we're still under the Dalton model. We're still under the solid sphere model. So at this point here, probably he had discovered about 40 or 50 pure elements. He had this notion, yes, atoms are things that are tiny, but you really didn't have the notion of protons, neutrons, electrons yet. So especially when we look at his organization on the periodic table, we're going to see that sort of demonstrated as he organized the periodic table. This fellow here, he organized what we now call our periodic table, this table that sort of lists all the different elements. Periodic table using, we'll just call them element cards. If you know the traditional card game Solitaire, that's essentially what he did. He had an element card here. He probably called it different names, but let's say this was carbon. He basically listed all the properties he knew about carbon. Carbon is a solid, the texture of it, is it very powdery, what's its melting point, what's its boiling point, what does it react with, and essentially what he had were a bunch of these cards here of all the known elements at his time. And all he tried to do was try to put these guys in order. Again, he wasn't working alone. Around this time here, we had other scientists developing some patterns already. Oh, these elements typically react together. They did the law of triads, the law of octaves, so 3s and 8s as well. But Mendeleev was the one that was credited with sort of putting it all together. So you can imagine for Mendeleev having a handful of these cards here, 40 or 50 cards, and trying to arrange them, trying to order them in some fashion that ends up making sense, that makes it easy to actually track the different element properties. In this case here, he demonstrates part of our IB learner profile. As he tried to arrange it, he did actually arrange it eventually by mass. This was probably not his first iteration. But one of the successes he's credited with was he sort of knew, well, our technology at this time here, we may not have actually discovered all our pure elements just yet. He actually took some risks in actually leaving some gaps in his periodic table. And this actually turned around and actually gave him something to study after. He would look for something that behaved like the other elements in his column, somewhere intermediate in mass between this one here that's a little bit lighter, this one here that's a little bit heavier. It actually gave him a little bit of control to actually look for a certain element with certain properties. So we'll just note down here, he did take several risks. So he's demonstrating that risk-taking nature. Several risks, several risks, leaving blanks on the periodic table. And for him, his reasoning for leaving blanks, like I mentioned, he believed at this point here there were some undiscovered elements. So if he didn't have a complete listing of all the cards, obviously there may be some that are missing, no problem. At least there's 3 elements that he discovered in this form. I think gallium was one of them. The other thing here was because the technology at the time here wasn't that great, even though we're going to see he eventually arranged them by atomic mass, there are a few places on the periodic table that the mass doesn't increase as we would expect. So he attributed it to perhaps in our experiments up to this point, there is an inaccuracy of weights or inaccuracy of a molar mass. So let me just give you an illustration of that here. When we look at our traditional periodic table, again, we sort of have the benefit of hindsight as we're looking through here. We know all about protons and neutrons. It's actually the core particles that actually make the element different. We see, as we mentioned, the number of protons increases as you go to the right. So does the number of neutrons, the other heavy particle in the nucleus. We would expect to see that the mass here steadily increases, but you'll notice here there are a few places, for example, tellurium and iodine. Tellurium only has 52 protons. He didn't know this. When we go to 53 protons, iodine should be heavier. And yet, when we look at the average mass, once we add up those neutrons, the average mass of tellurium was actually heavier than the mass of iodine. This part here was really strange. If he was really strict in following his rule of organizing by mass, he would have actually put the iodine first and then the tellurium afterwards. He demonstrated this sort of risk-taking behavior by saying, well, I noticed the fluorines, chlorines, and bromine, these ones here are all halogens, these ones here are all colorful gases. Iodine tends to react in the same fashion. He was able to be like, okay, even though I would have expected this one being heavy, the iodine being lighter, he actually switched it to maybe I have my mass wrong and maybe iodine really should fit inside with the rest of the column here. So he had demonstrated this sort of risk-taking nature, not only leaving the blanks, but just leaving room for some error. Maybe the data at the time isn't quite correct. Again, in hindsight, you should be able to explain to me how come this mass here is actually different in thinking about weighted averages and isotope stuff that we did in the last chapter. So that's what he did. He played with his element cards here. He was the one that was credited with sort of organizing our modern periodic table. They want you to know this term here. By organizing in this fashion here, there was a periodic law that the elements end up showing up. And here, all it says here, the element characteristics or element properties, how the elements ended up behaved, element characteristics and reactivities, how they actually behave chemically as well as physically. These ones here repeat. There's our main word for this chapter here. Repeat meaning periodic. It comes back again and again. We're going to get some trends. They repeat when arranged by increasing, so from smallest to biggest, increasing atomic mass. So if you arrange it from the lightest element to the heaviest element, don't just list them all in one single row. Start putting columns to it, especially elements that react the same in the same column. You have this sort of commonality and this trend that ends up repeating. Nowadays, because we're not under the Dalton understanding, the solid sphere model, we know because of isotopes, it sort of messes up our mass calculations. We know actually this atomic mass here is better said, let's do increasing atomic number, where atomic number specifically looks at protons and specifically looks at the element. So back with tellurium and iodine, which were slightly different in terms of masses, at least their element number was correct. The element number for tellurium is less than iodine, which means tellurium should have come before iodine does. So that sort of gave us the onset of our traditional periodic table. Let's just look at some of these trends that come out based on this periodic law. If you can just sort of sketch out a quick periodic table here. Just some terminology for us just to review. We have the hydrogen and helium as our first row. Rows on the periodic table, so rows always go horizontally left and right. Rows on the periodic table are called periods. If you can ask yourself, what do elements on the same period, let's say hydrogen and helium are on row 1, lithium, beryllium, and the other elements are on row 2, what does this row number actually indicate for the element? If you look at the Bohr model, we're going to do a lab on this very shortly, but in this case here, the period actually indicates for you the energy level, which is why back in chapter 2, we were able to say our s electrons and p electrons, our s electrons and p electrons, these ones here, I know they're s electrons because of the first two columns, but because they're on period number 1, we know these are 1s orbitals. Lithium, beryllium similarly will be s electrons, but being on row 2 are suddenly going to be 2s energy level. So either you talk about energy level, if you're thinking about the Bohr model, we're talking about sort of which shell that we're on. So say lithium, which is on row number 2, we expect the Bohr model will have 2 shells, and the second shell would be the valence electron. It does get a little bit messy when we get to the D blocks. We did this already here. Technically, we're row number 4. We should be energy level 4. The Bohr model should be 4 shells out. And yet, based on our electrical configuration stuff, remember we saw when the Ds first come in, these Ds here, not only do they come 5 rows on every floor, these ones here are only energy level 3. We still off-ball, so we all still build up from lowest energy first, but just take in mind, especially when we get to the Ds and the F blocks, they may not necessarily match really nicely with the period number. Periods are going across. When we say across, we mean left to right, whereas groups, traditionally they actually call them families. IB does prefer you when you count the group numbers. Yes, the alkali metals here are group number 1. This is this first column here, group number 2, so on and so forth. This would technically be group 3 to 12. we're counting group 13 as the boron column all the way over to 18. And yet on the periodic table, if we sort of ignore the transition metals because they do a different type of bonding, we could traditionally call group 13, we can call that group 3. The nice thing is because we have 10 elements in the D block, once I subtract those 10 or I ignore those 10 as inner electrons, those don't count as valence electrons, I could hypothetically call group 13 group 3 or group 18 group 8. So we'll see that in upcoming lessons here. Groups, or traditionally called families. If elements are in the same family together, they all look alike, they all behave the same. If you remember from your earlier science courses, the group number actually tells you the number of valence electrons. They actually tell you how many electrons are in the outermost shell. It's the valence electrons that actually do the bonding. So when atoms have to collide together and exchange electrons, share electrons, depending on how many I have on the outermost shell really determines the reactivity. So the number of valence electrons, and it also determines your reactivity. It determines how things behave, what are their chemical properties. So things in the alkali metal, if you haven't done this yet, try a Bohr model. Try hydrogen, first shell, 1 electron. I have 1 valence electron, making sense because I'm in group number 1. Lithium actually has 3 electrons, but by the time you draw the 2 shells that lithium has, it too only has 1 valence electron. So having that 1 valence electron puts you in the alkali metals, and it makes you that family. It makes you all behave the same. In upcoming lessons, we're actually going to skip down the alkali metals as well as halogens and noble gases. Because they have the same valence structure, we're actually going to be able to imply some of their properties and some of their reactivities. As I mentioned for today's lesson, I wanted to introduce to you 2 fundamental principles that will carry out through the chapter. Hopefully it will help in explaining for you this notion of atomic size again, as well as we'll get to in tomorrow's lesson, ionization energy. How come the ionization energy trend is, say, increasing going to the right and decreasing going downwards? So here I just want to introduce to you those 2 main principles. These 2 principles will be whenever they ask you to explain how come this element is bigger than this one, or how come this guy's electron is easier to remove than another guy, you want to be quoting some of these terms here. So this first term here, eventually we're going to see a guy called effective nuclear charge. Let's start off with just plain old nuclear charge, because we know that. So think about the nucleus. We know, again, we have the benefit of hindsight. We know the Bohr model is protons and neutrons. The particles in the core that are actually charged are these protons, right? Protons have a positive charge. So the nuclear charge actually just implies the positive charge from the protons. Sure, we do have neutrons as well, but neutrons don't give you any charge. They just come along for the ride. Because protons are indicated by the atomic number, the nuclear charge we usually use Z. We notice protons here have a positive attraction. That's the thing that's able to keep electrons around this nuclei. We know opposites attract, so electrons, given the option, if a bunch of electrons arrive at your hotel, electrons will want to fall to the closest shell, because in that case there, they will have the greatest attraction to that positive center there. That's why we off-ball, and that's why we end up getting a ground state of the element. What we're going to have here is, when we start considering the Bohr model, let's take a look at lithium again. Lithium as an atom has 3 electrons total. 2 of them have gone into the first shell. They are paired. Those are 1s2. Our third electron actually goes into the next shell. That is the closest spot for it. Unfortunately, it can't go on shell number 1 because it's been maxed out. In this case here, there's no doubt this electron on second shell has a negative charge. This negative charge here is still attracted to the positive charge of the nucleus. But what I want to imply to you here is the electron, although the lithium atom here has all 3 protons, all 3 positives to attract this outermost electron shell, this electron actually sees less than 3 positive from the core. The reason for that here is because this electron is on shell number 2, there actually are 2 other electrons that are closer than it. These 2 electrons similarly are attracted to the nucleus. But when these 2 electrons here are in those orbitals and they're sort of surrounding this nuclear charge here, they're sort of blocking out, they're sort of sheltering off. In words, we say they're screening off some of the charge of the nucleus. My student teacher used to use this analogy. Imagine someone famous comes into your room. Everyone flocks to see this celebrity. Everyone flocks to surround this famous person, this celebrity. the people that are closest will sort of be like the happiest because they're surrounding the celebrity. They're most attracted to the celebrity here. You may have been a little bit late. You may have ended up on the second shell here. You can also see the celebrity, but only in between the people in front of you, all in the rows in front of you, blocking out the celebrity. So although you can have some indirect attraction, some indirect glance at the celebrity, your view is actually screened out. In the same way, electrons on this shell here are actually blocked out. They're shielded by any inner shells. So let's just write this down in words here. Electrons on the outermost shell, okay? Outer electrons see, I'm just going to use the term see, or they feel an attraction, okay? They see less charge than the true nuclear charge. So although no doubt this lithium here has to have 3 protons, the attraction for this electron is actually going to be less than the 3 that we would expect. And in this case here, I'm just going to give you a little bit of hand-wavy math here. In total, this electron was supposed to see 3 protons. We were supposed to see all 3 positives, but what I'm going to do is I'm going to minus off any electrons on shells that are closer than me. These electrons with their negative charge, they're going to not only block out the positive attraction, because they're negative, they're actually going to repel me away. They're going to push me away from getting closer to the center as well. So we're going to take the true number. This one here is the actual Z, the actual charge that we have, and we're going to subtract off how many electrons are on shells that are closer than you. In this case here, we have 2 electrons that are closer than us, so we're going to minus off 2 electrons. It's like, effectively, we only see a +1 from the core. There still are 3 positives, but because of these 2 electrons, they block out 2 of the positive attraction. We call these electrons on inner shells, so inner electrons. We call these ones here screening electrons because they screen out the positive charge, they block out the celebrity, or you can also call them shielding electrons, shielding, again, blocking out. And eventually it leaves us, sure, the outermost electron still sees a little bit of the positive from the celebrity, the positive from the nucleus, but this guy here, we're going to give it a different name. We're going to now call this Z effective. So it's still Z, it's still the atomic number, it's still the proton number, but it's only the effective, the only the part having subtracted how much is blocked out, here's how much is left over. In the old textbook, they like to say Z effective here, they like to write that as ENC, and effective nuclear charge. Both ways are perfectly fine, but that's the name that we need to know for now. So effective nuclear charge, it's how much of the nuclear charge do I have remaining, having subtracted any inner shell electrons. So let's just look back at our periodic table here. So far, I'm just going to look at the left-hand side. Let's start off here with just hydrogen and look at this Z effective. Hydrogen is nice because it only has 1 electron. Having 1 electron means I'm already as close to the core as possible. The true number of protons was a +1. There are no electrons that are screening me. I'm going to have a Z effective of +1. I get the celebrity to myself, and I basically have the full attraction to this hydrogen. We just did the example of lithium here. Lithium, based on the Bohr model, has 2 shells. It has 3 outermost shells. By the time you put all the electrons in, 2 of them are inner shells, leaving you with that same 1 valence selection we talked about earlier. The math I did for you earlier, we were supposed to see all 3 positives from the center. We minus off the 2 that are inner electrons that are closer than me. We effectively get a charge +1. And as you're starting to see a pattern forming here, I'll do one more with you here. Lithium Sodium is the element that's right underneath it, the group 3 alkali metal. Sodium has way more electrons. It actually has 10 electrons. We do our typical Bohr model, 2 on the first shell. By the time we get to the second shell, we start pairing it by the 5th electron. Once we put those 11 electrons, sodium similarly has 1 valence electron. Putting it in column number 1, group number 1, at least that follows a nice trend. As you start looking at the effective nuclear charge, this leftover charge that we're supposed to see, the Z effective is given by the true number of protons. Lithium is element number 11. So we were supposed to see all 11 positives from the core, but what we're going to do is we're going to minus off any inner shells. The inner shells here will not just be the first shell that has 2. There's also 8 other electrons on shell number 2. In total, there's going to be 10. This is a little bit hand-wavy math here because electrons that are on different shells, say shell 1 or shell 2, will block out the proton with different degrees. but just for simplicity, we'll just assume that they're the same. 10 electrons closer than me means it leaves me again with a +1 charge. What pattern are we seeing for Z effective as you go down a periodic table? If you said here the Z effective isn't really changing, you would be correct. So in this case here, this Z effective, this leftover charge that we had, I'm just going to write down here, Z effective remains similar. They may not be identical. Like I said, it's a little bit hand-wavy math here, but they remain about the same. Sure, I have way more electrons, but now suddenly beyond another shell out, I'm blocked out by another full shell that sort of blocks out and screens out all those extra electrons that I had. Z effective remains similar. We're going to use patterns on the periodic table. So I'm going to say going down a group from top to bottom. And just sort of in regular English translation here, what we're saying here is the effective charge from the nucleus, so the leftover positive attraction that I see from the core, after subtracting or after considering, after subtracting any screening or shielding electrons, stays similar from top to bottom. Okay. So make sure you know the definition of effective nuclear charge. It's this notion of what is the real charge after you've subtracted off the screening one. After you've blocked out people that are closer than you, what's the remaining charge? We're going to look back at this feature in a second here. That's the trend going downwards. What's the trend for Z effective going to the side? So say I go from lithium, say we go to beryllium. Because beryllium is also on row number 2, we would expect both of them to have 2 shells. If you start with the Bohr model, you actually see beryllium actually having 2 shells, no problem. First 2 are paired, are 1s2. For Bohr model, remember we write them as separate. As we go across, we knew that the second shell could actually handle more than just lithium's 1 valence electron. We can fill more in shell number 2 before it maxes out. So beryllium's electron, the closest place it could be is a 2s2 electron. It's just second electron on beryllium. When you look at the math, however, beryllium here will have 1 more proton because we're 1 element heavier. I'm supposed to see all 4 positive attractions from the core. If you look at where the electron was now added, the electron is also equally on shell number 2. We're all the second row out. This second electron, although it will have a little bit of repulsion with that first electron in shell number 2, they're not going to block out each other as badly as, say, these electrons on shell number 1. So when you end up doing your math, you're going to say, truly I was supposed to see a +4 in mass, but I'm still only going to minus off 2 electrons that are closer than me. You'll notice that your effective charge actually goes up. So this one here, beryllium has an effective charge of +2. If you follow through with that math there, you're going to see boron has +3 all the way to +8, nicely corresponding with your group number. Notice this one here is an effective nuclear charge. This one here is not the charge this element gets when things bond. For example, noble gases, they pretty much keep to themselves. They don't want to react. They don't want to transfer electrons. If anything, they just want to keep to themselves. They're nonmetals. They might be able to, in the odd case, covalent bond. They don't really want to take this plus charge. What we're talking about here, say for neon as an example, we're not saying suddenly we're going to have neon +8. What we're saying is by the time we look at the outer electrons, neon was supposed to have all 10 positives to attract all the electrons, which it does. If I were electrons on this outer shell, I'm blocked out by just the 2 electrons on the first shell, plus 10 minus the 2 that screened me out. It leaves me, if I were this outer electron, it's like I still see a +8 from the core. So again, it's important for you to realize this is not the charge that the element gets when it bonds. This is just the leftover charge that we get as we go across. So let me just summarize that there. Going across here, left to right, the Z effective actually does increase. It doesn't stay the same anymore. Z effective increases across a period, which we know is synonymous with a row that's going left to right. And in this case here, it's quite simply because you have more protons. More protons, you do also get extra electrons, but those electrons being added to the very same shell, they don't block out each other as badly. So Z effective increases across a period. Our reasoning will be more protons and electrons on the same shell don't shield. We were only looking for electrons that are closer than me that actually do the shielding. So that definitely is already one of our periodic trends. This is a fundamental principle that I go through these first couple lessons. If you can quote for me something happens to Z effective, you can quote for me something about the size. So Z effective is one property. The other property I just want to end off for this lesson here is the notion of a Coulomb attraction or a Coulomb law. So a Coulomb force. A Coulomb force here is an electrostatic. It could be a repulsion as well, but I'm going to, just in the context of chemistry, we're looking at positive and negative as an attraction, opposites attract. So a Coulomb force is an electrostatic attraction between the positive nucleus, positive center, nuclei is plural, positive nuclei, and technically all the electrons, but specifically when we start looking at size again, we're worried about the outer shell. So Coulomb force in general is just looking at point charges. It's looking at if I have a positive and I have a negative, what's the force of attraction that these two have for each other? In our context in chemistry, our positive will be the number of protons, or it's going to be our Z effective. Our electrons will be these ones here, and we're going to specifically say valence electrons. Based on how much attraction there is between these charges, that's going to tell me something about how far out this orbital can get. We talked about in chapter 2, this orbital can't get super far out because there's a limited number of nuclear charge, in this case here even effective nuclear charge, so that's why the energy shells actually converge together, but at least there is an attraction between the two of them. I'm going to give you the formula. The Coulomb force is given by K, Q1, Q2, all over R squared. F, we know it to be the force. In this case here, it is a force of attraction. That's measured in newtons. K is going to be a constant. It's a proportionality factor in our universe. We're not necessarily going to need to deal with the math of this. We just need the general pattern that comes off this formula. These Q's here actually represent the charges. In this case here, I know positive and negative are an attractive force, so I know the direction of it. I basically figured out how positive is the center and how negative are the electrons. So those are my charges. In this case here, you'll notice based on the formula, as these Q's end up getting bigger, as I end up getting more protons or more electrons, these Q's multiplied together will be bigger. That'll end up increasing the force. So one conclusion of this formula here is the force is proportional to charge. The bigger the charges that we have, the more effective nuclear charge, the stronger the attraction is between them. And similarly here, the formula is not just the KQQ, we also have a divided by R squared. We're actually inversely proportional with distance. We saw this a little bit in chapter 2. As charges get further and further away from each other, it gets harder and harder for them to attract. As the radius, sometimes they put D for this as well, separation distance or R, as the radius itself gets bigger, we divide by a bigger number squared, the force ends up getting smaller. So based on this formula, we don't need to do the math too much based on this equation, but at least I want you to know this principle here. Force is inverse to the separation distance. The farther out things are, the attractive force is actually decreased. So these are two fundamental principles we're going to have, especially throughout these first couple lessons. Just let me hint at what this is going to give us here. We'll flesh this out a little bit more in tomorrow's lesson here. Basically, we said, looking at our Bohr models, hydrogen has 1 valence electron, lithium had 2 valence shells, sodium had 3 valence shells. Our Z effective really didn't change much. Even though sodium has way more protons, way more electrons, effectively, this outer electron sees the same positive one left over from the core. That would imply to you, if the charges are similar, you'd expect that the attraction is also similar. So in that case, you might imagine that the radius is actually the same. In this case here, Z effective doesn't really do a good job of this. Z effective, I know Z effective doesn't change, so we're going to write this out some more tomorrow. Although the Z effective is similar, that would have implied that the radius should be the same, right? Same amount of attraction, right? I see the same positive. We see better from the Bohr model. As you go down, I pick up another energy shell, and especially when I get more layers, I'm definitely going to be further out. Although Z effective is similar, we're going to have our atomic radius, our size, actually increase. Radius increases due to having more shells. So questions in this section will be, pick hydrogen, pick sodium. Who's larger? All you would say is you'd say sodium has a bigger radius because sodium has more shells. That's the trend going up and down. We're going to use Z effective a little bit more going across. As you go across, we saw Z effective went +1, +2, all the way over to +8. What would happen if over here, lithium's proton or beryllium's proton here, we only have +2 in the core. That's the amount of leftover electrons that we have seeing in the core. What would happen as you continue to step across? The center becomes +3, +4, all the way over to +8. The center itself is getting more and more positive. We're also getting more and more electrons on that second shell there, or whichever floor that we're on. We see that from the Coulomb attraction. If the charges are greater, the force of attraction is also greater. Yes, even though the nucleus itself is going to get larger, it's actually that attraction that gets stronger. So this effective charge, the leftover positive I see from the core, is bigger and bigger. It's going to end up pulling the shells in tighter, and we're going to end up seeing the radius actually drop. It's actually a notable decrease here. Again, we'll flesh this out a little bit more in tomorrow's lesson. We're going to see in our data booklet, if I can scroll right back to the top, we actually, in addition to our periodic table, which has the different molar masses as we used earlier, we actually have another periodic table laid out pattern, and we actually see the radius actually shrink. Going left to right, the radius goes 130 to 99 to 84, 75. It actually does shrink. The units that we're in is times 10 to the negative 12, or you can call these picometers. So, using those two principles of Z effective as well as Coulomb force, we can explain what happens to the atomic size and ionic size. We're going to come back on tomorrow's lesson to look at ionization energy and some other patterns on the periodic table. Thanks, guys. If you have any questions, just let me know.